Hello friends, this is our lecture number 4 in modern physics and relativity. And in this lecture we will discuss the length contraction, time dilation and the examples of time dilation as Muon Decay and GPS system, twin paradox, and also how the time dilation was used by in Hindu Puranas. So measurement of length and time intervals are affected by relative motion. And if we see one frame of reference is moving with some velocity v, and there is one another frame, fixed frame, and if a rod of length L naught, which is in this frame, moving frame, and the length was measured by the observer in this moving frame when it was at rest, so it is L naught, and L naught is known as its proper length also. So it will be x2 prime minus x1 prime. So this is the L naught is the proper length. And if an observer is now in a fixed frame and you want to see the length of this L naught from this frame of reference. So from Lorentz transformation equation, we know that the coordinates x1 prime and x1 are related like this, and x2 prime and x2 are related with like this. If the total frame is moving with some velocity v, x1 prime equal to x1 minus bt divided by under root 1 minus b square by c square, and x2 prime equal to x2 minus bt divided by 1 minus under root 1 minus b square by c square. And if we put these values here, we will get x2 minus x1 divided by under root 1 minus b square by c square, and L naught, this x2 minus x1 is the length L as observed by the observer in rest frame or fixed frame. So L will be L naught into 1 minus under root 1 minus b square by c square. So length is contracted by a factor under root 1 minus b square by c square, and this is also known as Lorentz Fitzgerald contraction, and the contraction takes place only in the direction of motion. Here is we can see that if the length of this photo or image is L naught, and if it is moving with some velocity, high velocity v, then we will see the contraction only in this side length, direction of motion, not in the another direction. Suppose length is contracted but width is same as when it was at rest. So length contraction takes place only in the direction of motion, and L equal to L naught under root 1 minus b square by c square. So it depends on the b, how much percentage will be contracted. Similarly, if we have a circle which is at rest, and if it is moving with some high speed, suppose 0.3 c, 0.6 c or 0.9 c, then we can see the change in the shape, and it becomes ellipse when moving at high speeds. Though there are some examples based on the length contraction. So how fast does a rocket ship have to go for its length to be contracted to 75% of its length? So here L equal to 0.75 of its original length, L naught. So if we put it in the formula, L equal to L naught under root 1 minus b square by c square. So L by L naught is given as 0.75. It is under root 1 minus b square by c square is equal to 0.75. So if we solve it by squaring both sides, and then we will get v square by c square, and now v will be 0.67 c. Similarly, one other example is there. An astronaut whose height on the earth is 6 feet is lying parallel to the axis of spacecraft moving at 0.9 c relative to earth. What is its height as measured by observer in the same aircraft spacecraft and by the observer on the earth? So first part is, for the observer in the spacecraft will be the height will be same because it is observer is inside the spacecraft, so L naught will be 6 feet. But this length or this height will be changed for the person on the earth. Means if the observer is on earth, then it will be contracted to L, or we can write using the length contraction formula. This L naught will look like L. L will be L naught under root 1 minus b square by c square, and if we put the values, L naught was 6 feet and B was given 0.9 C, 1 minus 0.9 C whole square divided by C square, and this, after solving this, L equal to 6 into this 0.43, 2.615 feet. So this is length is contracted for the observer on Earth due to that high velocity. Now another thing is time dilation. Again, the time intervals are also affected by the motion of the objects or relative motion, and a clock in the moving frame will be seen to be running slow, or it is dilated according to the relative motion or the transformation equations. And the time measured in the frame in which the clock is at rest is known as the proper time, because if clock is here and the t naught is its proper time, means between two events, t2 prime and t1 prime, it is t naught, and it was the time when this frame observer is in this frame, then this is t naught proper time here. But when the observer is at rest frame and it looks this time t naught, then it will be changed and we will get the formula for time dilation. So we have here t2 prime and t1 prime for two events in moving frame. So t1 and we need t2 and t1 here in fixed frame. So t1 and t2 are related with t1 prime and t2 prime with inverse Lorentz transformation equation, because prime values are known here and we need to non-prime value or t1 and t2 for, at the rest. So t1 equal to t1 prime plus bx by c square divided by under root 1 minus b square by c square, and here it will be for t2. And if we take the difference t naught equal to t2 prime minus t1 prime, this is t naught in this frame. So in fixed frame it will be t equal to t2 minus t1, and if we put this values t2 and t1 here and take the this under root 1 minus b square by c square as common, so we will have t2 prime minus t1 prime, bx by c square minus bx by c square, this will be cancelled out. So we will have t2 prime minus t1 prime, we can write t naught divided by 1 minus b square by c square, and this is t equal to t naught by under root 1 minus b square by c square. So that's why a moving clock appears to be slowed down by to the stationary observer. According to this relation, t naught will be divided by this, and this effect is known as the time dilation. And dilation means to dilate means to become larger. Here the minute or the hour will be longer. It will take longer time, so it will the total time will be slower here. So this effect is known as time dilation for the moving objects. A clock, this is an example, a clock showing correct time when it is at rest loses 1 hour in a day when it is moving. So what is its velocity? So if we know that there are 24 hours here on Earth, and if it loses 1 hour in a day when it is moving, moving means t naught is 23, on t is 24 hours, 24 equal to 23 divided by 1 minus b square by c square under root, and if we put solve it, and b equal to 0.286 c. So this is question based on the time dilation. Now we will see that this is not just a theoretical formula, but time dilation is a real time effect, and there are some experimental proof of time dilation are there, and we will see two experiments. These are time dilation was verified by decay of muon particles, and because existence of muon particles on Earth atmosphere or Earth surface, we will see next slide. And also there were some experiments made with some atomic clocks or very precise clocks, and they put these clocks in airplane and then see the effect of velocity on the time. So we will see Muon Decay is one of the real example of time dilation, and two scientists Rossi and Hall in year 1941 they measured the flux of elementary particle muons on Earth's surface, and they found reasonable amount of these particles on surface of Earth, and muons are created in upper atmosphere when cosmic rays coming from sun it collides with the air particles or air molecules. The muons are unstable particles and it decays into electron and positron. and these particles should not reach up to the surface of Earth because their decay time is very small. And in frame of reference of this particle, it can travel only up to 600 meter because the speed is 0.998 c, and the average life of these particles, muon particles, are 2 microsecond. It means 2 into 10 to the power minus 6 second. So in frame of reference of muon, it can travel only b into t, and it is 600 meter. But muon uh, should not reach to the earth because the atmosphere is around 9 to 10 kilometer from here to the surface of the earth, and they should not reach to the uh, surface of earth. But in frame of reference of observer on earth, the average lifetime of muon is due to time dilation t earth equal to t muon divided by under root 1 minus b square by c square, and it is 2 microsecond divided by under root 1 minus b square. B is 0.998 c square divided by c square, and this comes around 31.6 microseconds. And in this time, the muon particle can travel a distance b into t, that is b is fixed 0.998 into 3 into 10 to the power 8 meter per second into this time is 31.6 into 10 to the power minus 6 second in Earth's frame of reference. So it comes around 9461 meter or around 9 to 10 kilometer. It is around 10 kilometer. So that's why these muon particles, they can reach to the surface of Earth due to the time dilation effect. And one another real example was done on time dilation was by Hafele-Keating in 1971. They were two American scientists, and they have used three very precise atomic clocks. One was put in the laboratory, and another two clocks were put in the airplanes, and one of the airplane was traveling from east to west, and another was from west to east. And because the earth rotates from west to east direction, so in this case the airplane was traveling against the rotation of earth, and in this direction it is traveling with the following the earth's rotation. So that's why they have calculated using the time dilation formula of special theory of relativity, and also due to the height altitude, and it also gives some kind of time lag. In both the cases, they have got some time dilation of 273 nanosecond in this case, west to east, and east to west they got 59 nanosecond, and this using the formula. And when after this whole journey, they have uh, they have verified the three clocks, and they found the uh, time lag whatever they have calculated from the theoretical formula of time dilation, and they found it in real clocks also. So that's why they also verify the time dilation formula. And also in it was also verified in a particle accelerator in Germany, and they also confirmed that the moving clocks are slower, means the time dilation experiment was real. Now we will see the gravitational time dilation, and it was given by Einstein in theory of general relativity in 1916, and it is known as gravitational time dilation, and this is due to the gravity. And gravitational time dilation is because of the massive objects like Earth, and they create some kind of gravitational field around it, and it curves the space and time, and stronger the gravity, the more curve is there, and that's why the time is slower here, means near the earth the clocks are slower, and when it is at highest altitude then uh, the clocks are faster. Means on the surface of Earth, time is slower, and at high altitude, the time is faster. And clocks at higher altitudes, they tick faster than clocks on the Earth's surface. So this general relativity or gravitational time dilation is also we can see it in the GPS system. And one another example of time dilation is GPS system, in which the artificial satellite orbiting around the Earth, and these are at high altitudes. They are at a few thousand kilometers from the Earth at height, and also they are moving in the orbital, so they have a high speed also. So now there are two kind of time dilation in this case. One is due to the orbital velocity, that is v, and due to this v, the special theory of relativity tells that there is some time dilation t equal to t naught divided by under root 1 minus v square by c square. So the clocks in this moving satellite, they gets slow by 7 microsecond. If we do the calculation and using the velocity of this satellite, then there is some time lag of 7 microsecond is there. And also due to the general theory of relativity, Einstein gave one equation for also t and d tau equal to dt under root 1 minus 2 capital G m by c square into r, where this G is gravitational constant, m is the mass of Earth, c is the speed of light, and r is the distance or altitude of this satellite. So this will give us a time change, or due to this there is the difference of 45 microsecond. It is faster for the satellite clock. Due to this relativity, special theory of relativity, it was 7 microseconds slower, but due to uh, the altitude, it is 45 microsecond faster. So that's why there is a need of to compensate this time lag, and 45 minus 7, it is 38 microsecond. So there is some software which reduces this increased time of 38 microsecond in every 24 hours. So this is also one real example which is used in GPS system based on the time dilation. So there is a thought experiment in special relativity which is known as the twin paradox. If two twins, means they were born together, their age is similar, and at a time one person is on Earth and other person goes for a space journey with very high speed, and if he she travels long distance like in light years, many light years, and when she will come back, the other person or other twins, it is aged more as compared to the person which was on journey. So this effect is known as twin paradox, and this is due to the time dilation, because when this person was moving, the clocks, as we have seen that t equal to t naught divided by under root 1 minus b square by c square. So depending on this high speeds, the time gets dilated here for the moving clocks, and that's why the person is aged here, and the other twin have this is less than the person on the earth. So this was the twin paradox. So time dilation was explained in Hindu Puranas and Vedas thousands of years before the relativity theory, which was given by Einstein in 1905. And there was very uh, interesting story about the Revati, which was the daughter of King Kakudmi and wife of Balram. And Balram was the elder brother of Lord Krishna. And the story is that King Kakudmi could not find a suitable person to marry his daughter, and then he went to Brahmalok to solve this problem with Brahmaji, who was the creator of all the things and creator of universe. And he has blessing to visit many gods and visit many places. So King Kakudmi visited the Brahmlok, and when he reached to Brahmlok, he was told to wait for few minutes for meeting, and finally Brahmaji met him and gave him the blessings that go back to earth and you will find a suitable person on earth. And in few minutes of these uh, spent in Brahmlok, so millions of years have passed on the earth. It was around 27 Chaturyug was spent, were spent on the earth of these few minutes which he had spent, and they have spent on the Brahmlok. And 27 Chaturyug means one yug, Chaturyug means four yugs are there, and one yug is also of thousands of years. So there is a lot of time have passed on earth, and everything of that era was had already finished. And we can understand this by this calculation that 1 second of Brahmlok is around 100,000 years of the years on earth. So 100,000 uh, year on earth is around 1 second of Brahmlok. And when they returned from this journey from Brahmlok, then when they reached on earth, it was the time of Mahabharat, and then they found the person which was Balram for uh, marriage as suggested by Lord Brahma. So then Revati was married with Balram, and this is well documented and written in Bhagwat Puran, and that we can understand that in Brahmalok, time was running slow as compared to Earth, which is now known as the time dilation. Okay, thanks for watching this video. And if you have any queries or suggestion, then please write in the comment box. And previous video, we have discussed the Lorentz transformation equations and relativistic velocity addition formula. And in next video, we will see the relativity of simultaneity, and also we will see that how mass varies with the high velocities or variation of mass with velocity. Thank you very much.